First, let me say, well, as you can see, this project had many participants. It's basically joint with UC Berkeley and MIT. It was originally sponsored by Rich Jalen and then taken over by Rob Hunt. And we've recently transitioned the work and the results we've had to MITRE, who are now working on the next phase of implementation. Okay, so what's this session is traffic flow management, so this is really a traffic flow management kind of thing. It's a CDM thing, and but it's actually kind of out there. I think I actually had to give Rich Jalen credit, because when we first started this, it really was a very different thing, and even now I think it'll take time for people to accept it and to make it work, but I think it has a lot of promise. So what's the problem? And if you know anything about traffic flow management in the command center, you'll recognize this. So the command center, at least once in the beginning of the day, but usually multiple times a day, they have these strategic planning telecons where the command center gets on the phone with all the airlines, and they kind of talk about what the issues are for the day and talk about the strategy for traffic flow management for that day. And it's actually, it is a very good example of collaborative decision making. But if you look at how collaborative decision making has progressed in the last 20 years, there's been lots of advancements in terms of modeling and tools, et cetera. But this is still quite a low-tech operation. So what are some of the challenges of a strategic planning telecon? Well, it's verbal output. Operators that sort of yell the loudest have a disproportionate influence. They focus on specific parameters, like what's the scope of the program, is O'Hare included or not, rather than sort of more strategic performance goals. Different traffic managers may interpret what went on in different ways. So just generally, it's ad hoc and subjective. So that's one motivation for what I'm going to talk about. The second is next gen. So we actually are responding in a way to a fundamental part of the next gen architecture. So this is the current practice in terms of planning traffic management initiatives. You look at expected operating outcome, planned operational response execution, and then operational outcome. Well, in the next-gen architecture, there's an extra step in here, and that is setting service expectations. And this service expectation setting step is where the operators are supposed to have their input. So this is how they express their desires, goals, et cetera, for the system, rather than arguing about specific parameters about how you're going to do the GDP, what the rate will be, et cetera. So it's felt that this is a better way to have operator input. And so the idea is the airlines provide this consensus service expectation, and then the FAA develops an operational plan to meet those expectations. Okay. And just a final note about this is that part of the idea of establishing expectations is that you could come at the end of the day and you said, boy, this was a horrible day, delays, the FAA must have really messed up. Well, if it's very, very bad weather, you're not going to expect certain performance expectations. So the expectations are going to gear toward what the conditions of the day are, but they're also going to express operator preferences. Okay, so here's the broad concept. Formalize a process for flight operators to input their preferences into daily TFM decision making. So we have the flight operators. There's going to be this goal-setting mechanism with FAA mediation. And let me now say what is the output of that process. It's a vector of performance goals. And the three specifically that we considered, and you know, this was done after some thought, are a metric of capacity or throughput, a metric of efficiency, and a metric for predictability. I'll talk a little more about what each of those are. The idea is the operators, through this process, express this vector. That vector is then used by the FAA in designing the TFM strategies. OK, so these specific performance goals, and they're part of the broad ICAO set of goals. There's a list of about 10 such performance, I forget what the criteria. These are 3 of them, and we thought these were the most appropriate in this context. So capacity, the goal is to maximize throughput, avoid underestimating capacity, encourage quick response if weather clears early, et cetera. Efficiency is to minimize, so this is operator efficiency, so to minimize delay cost. So this can take on several forms, but the one that we most focused on here is that ground delay costs are going to be cheaper than air delay costs. The final is predictability, and as you heard Mark talk about predictability a little earlier, these two efforts informed each other. So some of the kinds of things with predictability is you'd like to announce GDPs well ahead of their start time, avoid overestimating or underestimating capacity, make program revisions unlikely. I don't know, I try not to spend too much time, but let me just give one anecdote about predictability. Back in the early days of CDM, Roger Beatty from American Airlines is sort of one of the godfathers of CDM. And I remember he gave a talk at a NEXTOR performance workshop once, and he said, what are all the sources of predictability? And he put about 5 things, and they were all on my list of sources of uncertainty. Then he put another one and says, what the FAA will do. Well, see, I was thinking like the FAA. What the FAA will do is not an uncertain thing to the FAA, but it's a huge uncertainty to the airlines. So, some of these, some of the way FAA does things can really impact predictability. OK, just about the performance goals. So just the numbers I'm going to use. 1 would be perfect performance. 0 would be worst performance. And I'm not going to talk about specific metrics, although obviously we use some. So the system is only going to allow goal vectors that are feasible. So you say, well, an airline said, what is your goal? Well, you say all at once. I want perfect in everything. Of course, this is not going to be possible, perfect performance across all dimensions. So we're going to be looking at vectors like the ones you might see here. The other thing, and this is what the system is meant to do, is to try to force the operators to make trade-offs. So for example, an operator might have to choose between these 2 vectors, and so this one says reduce capacity from 0.91 to 0.86. That means the throughput you're going to achieve is reduced, but efficiency is going to be. So you say, I'm willing to reduce throughput if I can increase efficiency. So that's the kind of trade-off. So maybe American wants the one on the left, United might want the one on the right. OK, so here's sort of a basic view of a snapshot of the system. We're going to have a set of candidate performance vectors. So here's a list of 3 there. The fundamental process here is it's actually a voting process. So, it's not a standard voting process. It's actually I'll explain it in a minute. It's actually a different kind of somewhat novel voting process. But you don't vote, you grade. So the airlines are going to grade these vectors. So grades, let's say, are in % between 0 and 100%. Based on this process, the system will come out with a consensus vector. So the definition of consensus is it's a vector that's output from this voting or grading process. OK, so let's see, what is the process? So we're using a process called majority judgment. It's a voting, grading mechanism that's been developed over the past 10 or so years. It's actually a voting mechanism that you can use in an election where you have many candidates and you want one winner through one round of voting. It's actually used in some elections in Europe. The idea is if you had 10 candidates, you wanted one election, you can use this process, one victor, you can use this process to come up with one victor without having to have runoff elections. All right, so let's see how it works. So let's say we have 6 airlines. Those are like our 6 voters, and we have 3 candidates. So a candidate is a vector. It's one of these 3-dimensional vectors. And they can have a grade, which is a percentage. So there's 3 example candidates, these vectors. So how does the process work? Well, each voter, each airline is going to grade each one of those candidate vectors. So American might grade the first one 98, the second one 90, the third one 79. United might give them different grades, et cetera. After the grading process, we're going to form this following table. So the rows are the vectors. What we've done here is we've taken the votes on the first candidate or first vector, and we've ordered them from highest to lowest. So one airline voted 100%, another 95, another 94, another 90, et cetera. The second one airline voted 90, 88, 87, et cetera. If you look in this column, these 3 votes were not necessarily given by the same airline. So maybe United voted 100 on the first, 87 on the second, 93 on the third. But we've just ordered them in this way. Each row is ordered differently. We then choose we assign a grade to each vector, which is the lowest grade, such that a majority of, actually the highest grade rather, such that a majority of the voters would give at least that grade. So majority in this case is 4. A majority agree that the first one has a grade of at least 90. A majority agrees that the second one has a grade of at least 85. A majority agree that the third one has a grade of at least 88. So therefore, we assign a 90 to the first one, an 85 to the second, and 88 to the third. The winner is the one with the highest grade. So the winner in this case is the first vector. It has a grade of 90%. Now, as you can imagine, there could be ties. And in fact, in certain kinds of situations, there would be lots of ties. And there's a tie-breaking rule, but I'm not going to go into that. But it's sort of based on a sort of an iterative application of the basic principle I've illustrated here. OK, so that's the mechanism. You could see how it could be used if, the M's could be candidates for president. You could have 10 M's or 5 M's or whatever. But, it's the same idea, except we're using it here to vote on vectors. OK, so what is the challenge in the application of a majority judgment to service level expectation? We just voted on 3 candidates. The question is, where did those candidates come from? Given conditions on a particular day of operations, what are appropriate possible goal vectors that should be presented to flight operators? In concept, there will be many, even an infinite number of possible vectors that represent possible trade-offs among the performance vectors given and the weather and traffic conditions. Thus, challenge 1 becomes the problem of representing the space of performance metric trade-offs for the TMIs, the traffic management initiatives under consideration. And then challenge 2, so we have to sort of, given a day, what are my possible vectors? The second challenge is, given some representation of the space of possible goal vectors, what is the process for choosing among these the ones that the flight operators will grade as part of the process? OK, so here is sort of a basic illustration of the process. So it's actually an iterative process, so you're going to vote more than once. So the idea is you start off with an initial set of candidates. There's this voting, so you have, say, an initial winner. But then based on that, we're going to look at the winner is, how the airlines voted, and we're going to generate some new candidates. So we might go around this loop a small number of times, say 3 or 4 times. and think of how beautiful this is. It's like a presidential election. We go through the election, we get a winner, and you say, I don't like that winner. Let's generate some more candidates. We all wish we could do that, and since we all wished it, we decided to do it for this project. So maybe they'll adopt it for our elections in the future. Anyway, so that's this iterative process. One small part of this is that there'll be airline weights, which means not all airlines are, so the idea is if we're planning a TMI into Chicago, well, you know, United has the most operations in Chicago, so United should have a bigger weight than some other carriers. So there'll be a weight, and the weight is like a number of votes. So, you know, maybe United gets 20 votes, American gets 15 votes, et cetera. So the idea is that airlines are weighted based on some measure of their influence on the system, or their sort of stake in the game in that particular case. The other thing, as I said, of course, we have to say, what is the space of feasible vectors? And I'll just mention that and this is a major piece of the research. I'm not going to talk about it, but there's you know, basically we look at TMI, in particular, ground delay program performance. We look at weather conditions, et cetera, and we've come up with a space of feasible vectors given the conditions of the day, et cetera. And this is actually a very challenging problem, but we've done, you know, some you know, basic research on that, and we're able to use that in sort of initial testing of the system. Just a comment there, you say on a very bad weather day, the possible vector values might be lower than on a good weather day. So on a good weather day, you could achieve closer to perfect performance. On a bad weather day, not so much. But I'm not going to talk about how we do this, just to say this is a big piece of the work. Okay. So just to kind of summarize some of the features. So as I said before, airline votes are weighted by number of flights involved in the TMI. So, you know, and by the way, this could be applied in different contexts. It could be deployed for an airport, like for a GDP. It could be applied on the nationwide basis to get to an overall TF strategy for the day. It could be applied for a metroplex, et cetera. That's the concept. Obviously, we haven't gotten that far. But, you know, if it was nationwide basis, somehow it would be based on overall, the weights would be based on overall airline involvement, regional basis, number of operations at that airport, et cetera. So the voting process is iterative, as I said. And let me just check the time here. Okay. You know, you might say this iteration takes a long time. I mean, certainly initially, there's humans involved. We view the voting process, at least in the long run, as becoming automatic. In other words, the airlines would have agents that are voting, so that even though this is an iterative process, it would be very quick. Only feasible candidate vectors are allowed. That's what I was saying. We have this process of developing a set of feasible candidates. It's certainly the case that the airlines may develop their own tools to assess how different candidate vectors affect their individual business operations. And multiple applications of counsel might be used as conditions change and could be applied to a nationwide or regional problem. That's what I said earlier. By the way, I didn't mention the name, counsel, consensus, service level expectation setting. All right, so what are some of the significant research components? The process of generating candidates and the iteration mechanism, the definition of the space of feasible candidate vectors. So those are two problems I've mentioned. So by the way, the process of the iterative process, the idea is when we go through an iteration, we actually estimate the sort of value function for an airline and use that in generating new candidates. So we generate candidates that are likely to be chosen by the airlines. I mentioned the problem of defining the space of feasible candidates, understanding user impact and benefit mechanisms and gaining user acceptance, modeling the benefit mechanism and the impact on flight operators, and then modeling user voting and grading behavior. So one reason majority judgment is, there's a whole book on it about why it's reasonable, and it's a voting mechanism where the voters are motivated to vote in a truthful manner. That is, if they like this 100%, they vote 100%, and a little less, they vote 90, et cetera. So there's a whole theory about why this is a good voting mechanism. But in this context, we have to sort of validate that with simulations and other analysis. OK, so we evaluated it using multiple fast time simulations. These employed historical GDP data, also a complex operational response model, developed at MIT to support various airline studies. We also held a human-in-the-loop simulation that included participants from the FAA and air traffic specialists several airtimes. And the fast time simulations were used to assess benefits. And the HITL to gauge user response and acceptability. So what are the benefits? Well, less time spent by the airlines and FAA on strategic planning, telecoms, and related activity. Improved flight operator performance on day of ops, reduction in cost due to delay cancellations. So the operators are giving their preferences to the way these are planned. General improvement in operational performance, smoother planning, better service. This is sort of the goals. And then more equitable treatment of flight operators. So the idea is this is a process, a transparent, well-understood process where everyone has their sort of appropriate input. Just a snapshot of one performance study, and these are sort of average results. This was for San Francisco, but it's kind of viewed as averaged over several. This is for GDPs. So compared to historical data, there was a reduction in ground delay, reduction in passenger delay. By the way, to get this is a very complicated simulation that involved airline response models, estimates of airline cost functions, et cetera. So this is not a simple, coming up with this is not simple at all. It involves some complex airline response models. And an increase in airborne delay. This corresponded to a 4.2% overall reduction in airline operational costs. Basically, if you see that, it says when we took into account airline preferences, they wanted the FAA to be a little more aggressive. So you could be aggressive by maybe having higher rates, maybe starting the program a little later or ending it a little earlier, et cetera. So you get a little better, less ground delay, maybe more throughput, but you might at the expense on the average of a little more airline delay or airborne delay. Some feedback from the HITL. First of all, this is kind of a far out concept. By the way, in fact, I kind of forgot to put this slide in. There's a little missing piece I didn't even mention, but the output of this is that vector. You then have to have a process for designing a TMI or a GDP that takes that vector and turns it into a GDP that tries to achieve that vector. That is not, that piece of so that's like performance-based ATM. We have some initial ideas on that, and NASA is working on that. So that's a piece of the problem that we have not solved, although we had we simulated its solution in this project. Anyways, this is a very different way of thinking. So initially, we thought the airlines might think it was, we were sort of in another universe, but airlines get it. The airlines understood that these trade-offs either are being made implicitly or explicitly. So the fact that these trade-offs are being made when the FAA and when they do GDP planning, they understood that that is absolutely what's going on. So they appreciated the approach, although they certainly didn't say, we're going to use it, we're going to be able to use it tomorrow. But they understood the concept, and they thought it brought some new novel features to the GDP planning process. They actually suggested a broader role for council should be considered and to use the majority mechanism for totally different kinds of things. 5? OK. And then some multiple applications of counsel for the same TMI could be valuable, and I've said that before. The extra burden on flight operators caused by counsel usage, and consider alternate ways of determining flight operator weights. So these were some of the things, feedback we got. So just a summary of the benefits. It's better focus on airline priorities, fair and more inclusive decision making. It's a goal-oriented process where performance criteria are clear to the flight operators, and more consistent with decision-making process where decisions are less dependent on managers' experience and personality. I think that's it. Yep. Okay.
Thank you.
So when you get put at the end of a program like today, you have only two thoughts cross your mind. The first is you think you may be at a wedding feast and they're saving the best wine for last. Or you think maybe you're the black sheep in the family. But anyway, I'm happy to be here. Glad you stayed around for my talk. I hope you can say that. Actually, I hope you can say the same after I'm done. I'm JP Clark. I'm from Georgia Tech, and I give talk about some work that I did with Bosun Kim and Leonardo Crucial. This is not a NEXTOR funded project, a NEXTOR inspired project. Part of the project was funded by American Airlines, and the other part was funded by the Brazilian government, but they don't know it. So what I wanted to talk about was talking about some of the gaming issues in CTOP. And what I wanted to do is basically provide some motivation for why we're doing this work. Give you some background on CTOP, which I think might be preaching to the choir in this room, but I'm not quite sure. Talk about the research questions that we tackled. Then talk about what some algorithms we came up with for determining what the optimal trajectory options would be for a CTOP without gaming. And then talk about some of the gaming issues that we've been exploring lately. And then finally, close with a slide about implications. So this is sort of everything, air transportation is a critical enabler of global economy. We always have to be reminded that this is a strong correlation with gross domestic product. Air cargo is a leading indicator of economic activity. There's a lot of jobs being produced, like ours. And the thing that's always interesting in my mind is that it's one of those things where if you look at across the globe, cities are usually near or next to an ocean-going navigable waterway. And there are very few exceptions to that, and those were basically built around train routes. But aviation has opened up places where you didn't have either water or railways. And so future economic growth will require significant improvements in efficiency and also in capacity. So with that said, let's move to the en route here. And we basically have congestion everywhere. And we've talked about congestion on the surface, terminal area, et cetera. I want to focus in on the en route. And basically en route is congestion is due primarily to either high demand or severe weather, primarily. I mean, there's other things like navigation outages, but those are more rare. And there are two methods traditionally employed to address these en route congestion. The first would be holding flights on the ground. Second would be rerouting flights that are airborne. And then traditionally, we've not been able to do both of those together and truly maximize this throughput by actually having both levers going together. So in recent times, FAA has introduced CTOP. For those who don't know, the Collaborative Trajectory Options Program. And basically this was designed to address this shortcoming. So you can actually look at both ground holding and multiple routes at the same time. And this is particularly important for en route congestion because you have what are called flow controlled areas, flow constraint areas, or basically which are, if you want to say surfaces, 2D surfaces in space, where airplanes are going to fly through. And you can find multiple one of these across the nation. And flights going from many origins to many destinations might have to go through this one common area. So that means by default, it's a combinatorial optimization problem, which is a lot of things you have to think about. And the philosophy that we've used in CTOP is basically an extension of the ground delay program, basically using the ration by schedule framework and the principles there. But the big difference is that it requires considerable consideration of significant numbers of combinations and permutations. And problem is that this has proven to be a challenge for many airlines, simply because they don't have the capabilities in-house to consider all these things in there. And so there could be a debate afterwards about whether or not they should have done more, whatever. But the fact is, it's a pretty significant problem for which there are no tools. So let me talk a little bit about how CTOP works. Basically, as you're doing a ground delay program, where's the laser? Bottom. How intuitively obvious. All right, so you have some en route congestion. You'd basically then issue a CTOP, just like in a ground delay program. The airline would respond. Now here's the issue. In a ground delay program, you basically say when you want to have a slot. For CTOP, for every flight, you have up to 5 options. And these options are ranked with a weighting in terms of time that tells you when the first option is preferred or should be rejected, and you move to the second option and so forth. So if you think about an airline that has maybe 100 flights going through 3 or 4 flow control areas, right? And 5 options for each of those. Think about all the combinations and permutations you got to think about. And you have a continuous variable, which is the holding time, and also the almost continuous variable about the route you're going to fly. So it's pretty extensive. And then once you have these, the FAA has a system which based on preference, the earliest time of arrival at the closest FCA, and then you basically get allocated. You can do substitution and compression, similar things to what you do in GDP. But the big step here is this. How do you decide what to submit, right? And so here's what you'd have to do for a CTOP example. So here's a flight going from Chicago to LaGuardia. You have 3 routes, one through this FCA, another one through this FCA, and this third one is called a no slot, which basically I'm going to ignore all this congestion. I'm just going to fly around it, right? Obviously, if the FCA is very wide, at some point the no slot is not an option because it's going to take too much fuel and the airplane probably can't make it. So you can hear it says, look, this is my preferred slot, route, or trajectory 1. After 30 minutes, I prefer to go to number 2. And then after that, after 40 minutes, I prefer a no slot. Okay, so that's basically a way, and the FAA uses these to come up with a relative cost to decide when to go, basically, so this one is 30 minutes preferred over this one, and this one is another for 10 more minutes, right? And so you can come up with a weighting factor based on delay and your relative trajectory cost for how valuable that flight is to you. So it's just a way of saying, you give me 5 options, rank ordered, with a weighting to tell me how valuable it is to you.
JP,
yeah.
The 30 minutes and the 40 minutes, those are ground delays, right?
Right, yes. All right, so how does it differ from GDP, you might ask? So here you determine the flight includes in CTOP, determine flights that are part of CTOP demand but are exempt, assign trajectories to the exempt flight. So if you have a GDP before, GDP takes precedence. And then what's left, then you allocate flights based on rank them based on initial arrival time at the CTOP. And what the definition of the initial arrival time is the closest, the earliest FCA that you're going to reach. And then you basically rank all the flights, and based on the weighting factors, you determine how the flights are going to, what times delays are going to impact, and what routes they're going to be given. Okay, that gets sent back to the operator. So from an airline's perspective, you have a question. Given all these options I have, what should I submit? What's the best thing for my business to submit? So the first question is, what should I submit to the to FAA to get the best slots? What's the definition of best slots? And then once you have that, how should the flights be actually assigned to slots? Because you can make substitution within your own airline amount of slots you have to increase your business decision. So this question leads to, how should I do it? But there's an underlying thing, which is, what infrastructure do I need to have in place to actually be able to do this? And then the second big question is, how should an airline try to game the system? Or should an airline try to game the system? Sorry. I'm not suggesting that they should. All right, and so what's the best strategy given all the possible actions that other airlines can make? So with that, let me focus in on the optimal trajectory problem. So what we did, so this basically, American came to us and said, we recognize that CTOP is coming on the road. We've put together a first response, which we're going to deploy because there's a deadline coming, but we'd like to think more about what should the second generation be. So we thought about it for a while. This was a very good collaboration because there were 3 folks at American Airlines and Bosung and I, and we basically worked as a collaborative team. And we came up with a two-stage algorithm, which seems to be my history of algorithms, always the decomposing. The first stage is basically find the best slots, given the capacity constraints and the likely action of others to minimize cost. And then once you have your slots, then find the best slot assignments, given the slots from the first stage to maximize revenue. Sounds familiar, right? It's in this one, like how we do airline scheduling, right? So basically, you have a set of routes, constrained capacity areas. You have a slot allocation optimizer, which tells you how to get your optimal slot, what your optimal slots are, and then you can figure out what to send the tasks based on that. And then you have a slot assignment algorithm to basically figure out how to assign your flights to the slots you've been given to meet your business objectives. So in the first stage, we're going to find the optimal FCA slot allocations that minimize total cost for the given set of aircraft within the planning horizon, the definition and capacity of the flow constraint areas, and a set of trajectory candidates by considering expected action of others and possible trajectory combinations. So what we did was we utilized the greedy algorithm first, which we basically said, well, you know, for a given FCA, you could have multiple trajectories. But the reality is you're going to take the best one or the earliest one for that FCA. So you can basically reduce that set. So that was the first thing that we did. And then once we have that, then we basically looked at all the possible combinations of trajectories. So we basically set the flights, sort flights based on the earliest IAT, regardless of the FCA, and that's how the FAA works. And then we basically looked at all the combination of trajectories and figured out the ones that made the best cost. So as you can probably tell, based on this example, things start to blow up really quickly, right? Because it's going to scale with the number of flights and the number of FCAs, because for each FCA, you're only picking one. So you can start thinking about, for 100 flights, the whole lot of trajectory combinations you start looking at. So what we basically did, and here's an example where you can see the available slot at FCA 1 is at 8 o'clock, 8:10, 8:20, 8:30, and 8:40, and then FCA 2 had 8:07, 8:18, 8:27, 8:36, and 8:45. And if you look through here, you can trace that path, and you can see that this basically gives you the lowest cost. Okay? Now, if you made a slight change up here, right, you could increase your cost slightly, but you could also, let me put that PC word, you could also penalize your competitor greatly with only a small increase in your own cost. So there's some potential here for gaming. Let's getting towards the end. We'll talk about that at the end. So, and here's another example where you have a small change in the slot allocation, and you basically see that the path that you get is going to be different. Okay? So it's quite sensitive. The optimal is quite narrow, flat. So what we do then is basically say, once we have the optimal trajectory, we can actually, because the combinations are going to be increasing high, the combination is going to grow large. We want to basically establish some sort of a rolling horizon. And in aviation, rolling horizon tends to be very useful because after a while, the amount of swaps that you can make, actually, the cost of making a swap between a flight at 8 o'clock and a flight at 8:30 becomes very, very high. Or between 8 o'clock and 9 o'clock. So it tends to basically, the number of combinations tend to naturally die down based on cost. And so we decided to do a rolling horizon where we basically have a time window, the classical thing. We would roll along halfway, freeze the first half, then basically solve the next one on overlapping. And what we found interestingly was this, that we played around with the, don't ask me, the students came up with this idea of chunk size, so chunk stuck. So it's basically the width of the time window, it's called a chunk. And so we looked around and looked at different chunk size and basically looked at also different moving strategies where you move a third of the way, halfway in the freezing horizon. And what we found was we had a very, very flat computational time up to about 20, a chunk size of about 20. And the cool thing, which was one of the well, not the happiest day of my life, but one of the happiest days, was we actually found that with our solution technique, we were basically converged really close to the optimal after about 13, 14. So we had that zone between 15 and 20 of a chunk size where we knew we were getting close to optimal across a whole bunch of different, the sensitivity with chunk size and sliding window, and we were able to compute it in reasonable time. So that's just the first part. And then, and I had some slides where I talked about the optimization problem with branch and bound, but Cindy recommended that I should not put those slides up, so I took them out. So anyway, so in the second stage, you want to find the optimal solution that satisfy the capacity query, minimize total cost for the given slot allocations, set of schedule of flights by swapping the slots internally, all right? And then, I should be maximizing revenue, there's a typo there. I can fix that. So, and basically also doing route outs. So what we actually did, and I won't go into details of this for the interest of time because I want to get on to the discussion about gaming. What we basically found was we were able, this is the baseline solution if the airline was basically going to submit what they do now, their preferred route. This is the solution you got in terms of after the first stage, and then the ability to swap internally gives you a much bigger benefit than actually allocating the flights. So the two-stage algorithm, basically you can see here for like a 700 flights, you drop the average the arrival delay costs from 120 hours down to about 40. So it's almost 1/3, 2/3 drop down to about 1/3 of the value. So that was it for the first thing. So the other question is, as you saw, that the number of combinations and the path through the combination tree was very sensitive to what you picked early on. So there's opportunity for you to penalize others with only a minimum cost to yourself. So that led us to think we should look at some of the gaming issues. So Bolson graduated, he's now working at American Airlines implementing this. And I had a student come from Brazil and he said he wanted to work on anything. So I said, hey, anything, free student, that's good for me. So we decided to look at the gaming aspects of this. So basically what happens, if you think about it, at the time you're doing your CTOP routes, you don't have really good visibility into what the other carriers are doing, right? You only know afterwards, right? And you also, of course, you have uncertainty about what the demand is going to be and what the weather is going to be, et cetera, all that stuff. And so, all right, so one rational assumption you could make in this thing is that, you know, if you have any information, the airlines that are going to operate are going to do something like they're going to introduce their preferred slot, or they're going to introduce their no slot, which basically I'm going to fly around this thing. So that's one rational assumption. All right. I'm going to use a keyboard from now on. However, airlines could do something else, and they could even game the system. So the question is, you need to consider a range of actions of the other airlines and also what they could do in response to your gaming. So the key question, obviously, is there a Nash equilibrium, right? And Nash it's a good question to ask this week because he's on everybody's mind. So here's a case where we looked at a bunch of airlines where you have 2 airlines with each at 100 flights going through 2 FCAs. And we were basically looking at what would happen if airline A sent either no slot for all their flights, 1 trajectory plus no slot, because no slot is always the default option, and 2 trajectories and no slot versus airline B doing the same. So these are all the combinations of each of those. And these are the costs. What you'd see that if airline A thought that airline B was going to send no slot, then that's its optimum decision. And if airline B, in parallel, thought that airline A was going to send no slot, then that would be their optimal decision. But the reality is that they're basically, by making their own thing, they're actually in this bottom corner. Use this for the laser. And the question is whether this is a Nash equilibrium. You can actually study it by saying, okay, if this guy moved, right, basically, you could improve, but then this guy can basically make a movement here to, this is basically A, and then B can make an improvement here, right? And so you can actually go on and you basically end up chasing yourself around the thing. At some point, you basically come back to that corner and say, that's the bet I'm going to stay. So we said, let's look at this over the case of a demand scenario, or set of demand scenarios where the proportion of flights for airline A changes. So it could be 50-50. Airline A could have 2/3, or airline A could have 3/4, right? And for each of these cases here, you can basically define a bunch of scenarios. Where basically in the first half, you have airline A would have 25 and 75, and then you can have it reversed. So 75, 25, 75, 75, 25, and then this one would have 50, 50, 50, 50, and this would be even. So we're trying to look also, not also the overall fraction, but how that fraction of flights are distributed. So one airline might be heavily loaded to the front, one might be heavily loaded to the back. And you can see that distribution here throughout. So these are all the scenarios that follow for each of these cases, okay? And so what we did, the computer is slow, huh? All right. So assuming airline A only knows this, which is basically airline A only believes that B is going to do no slot, can we come up with a solution? How would this affect the decision first to do no slot, one trajectory plus no slot, two trajectories plus no slot? And fourth, can we come up with an optimization scheme that determines what's the best number of trajectories to put in based on what we know about game theory? So that's the fourth option. All right, so these are all the cases here where you can think of, this is case 1, scenario 1, 2, and 3, and you can look at all the combinations for each of these. So we then created what we call the single game CTOP optimization function with the following payoff, which is basically the amount of delay in minutes for airline A for a given case, a given scenario, and a given move by airline A. And basically where airline A is give 0, 1, or 2 for no slot, 1 trajectory, or 2 trajectory, when moved by airline B is equal to 0, no slot, okay? And then we can then calculate some other variables where basically is the estimated cost for each of different scenarios, the deviation from these scenarios from the baseline that we just computed, the estimated mean delay for each case, and the relationship, the differences between the cases, so how sensitive the different cases are to each other. And I won't go into the details of this, but basically with that, you can come up with some expected value, and you can decide whether or not you should go with 2 trajectories or 1 trajectory based on the value of this function. And so what we end up doing was we evaluated the no slot, the 1 trajectory, the 2 trajectory, and our optimization function, how well it did perform. And we had 100 rounds, basically Groundhog Day. We had a CTOP from hour 6 to 8. We had about 3 or 5 aircraft per 15 minutes. And we actually created a scenario based on a bunch of real flights going to the New York metropolitan area from the big Miami, Dallas, Chicago, San Francisco, Los Angeles, Las Vegas. I don't know how come Atlanta wasn't in there, but anyway. And so what we found was we computed these PDFs, or it should be more like frequency curves, for basically what the solution would look like across all the different rounds. And then what we found was that you look at the delay, this is basically with no toss. This is what it would look like if you basically sent 1, and this is 2, and then you can see here that the OR optimization function basically mapped well to what would be the optimal over all these scenarios, which is to send 2 CTOP, 2 trajectories. However, what you also saw was that in the specific cases, our algorithm was able to perform quite well. In fact, it was better than just basically sending, either 1, 2 all the time. But using our algorithm was actually outperforming the others. And so with that, we were able to see that we were either equal to across all the cases or better than in specific cases than all the other ones combined. Okay? And so, oops. Good Lord. All right, so the short answer is this, that the Nash equilibrium can be achieved. However, the probability or the proportion of times that the given strategy is optimal varies the pace of the structured demand. So in a case where it's 50-50, it's a majority of the time, more than 3/4 of the time, it's best to send 2 slots. For both aircraft, the Nash equilibrium is for both airlines to send 2 slots. If, however, airline A has 2/3 and airline B has 3/4, 1/3, sorry, oops, 3/4 over there, 1/3, then it's marginally better to send 2. And then when you have 75-25, it's about half and half whether or not you should send 2 slots. And then this is basically, over all cases, it's better to send 2 slots than 1, 2 trajectories than 1 trajectory. So, since I only have 4 minutes, right? 3 minutes? So, sound decision making requires basically an optimization algorithm, which airlines really don't have. Game theoretic decision framework to consider all the combinations. Nash equilibrium can be achieved, but the proportion of times is optimal based on, depends what you should send, depends on the fraction of demand. And the Nash equilibrium is often weak, and this is a discussion that Mark and I had. There's an opportunity here for airlines to take a little bit more cost and penalize their competitors greatly. So there's some stuff to be investigated there and how you go about it. And with that, I'm done. Sorry.